Hello and welcome. Today we're going to talk about the gradient operator. Okay, so what do we mean by an operator? So we've heard of differential operators. Differential and integral operators. So an operator is typically defined as some sort of operation done on a function to output a different function. So you can think of an operator as a function of functions, right? So the input, rather than being a number, is a function, and it outputs a function. So of course we know certain certain operators. We know that ddx is such an operator. If I take the derivative of ddx, you can think of ddx as basically an operator. And it outputs f prime, right? A different function that somehow derived from the original function. And we know in calculus that f prime gives us lots of cool information about f. All right, so with that piece of nomenclature laid out, I want to talk about an operator for multivariate functions. So consider f of x comma y is equal to z, or f of x comma y comma z is equal to u. So of course this is in the two independent variables, and here's the 3D independent variables. Either case, we can define this thing. We're going to define what we call this upside down triangle. This is given a couple names. It's called del, or grad, or gradient. Okay. And it's equal to a vector of partial derivatives. So this is in the 2D case. And the 3D case is similarly defined. All right, so the idea here is that grad, this grad thing, it's not lambda. Grad is not a vector of numbers. Rather, it operates on functions and outputs a vector function of partial derivatives. Okay, so let's just give an example. Let's say I have a function f of x comma y is equal to we'll say 1 minus x squared plus, actually let's go with minus y squared. Right, so here's an operator, here's the function, and then of course your f would be, here's the partials like that, and then you have your function sitting next to it. And then what you do is you effectively just distribute in f to each one of those, and then you get the partial x of 1 minus x squared minus y squared, and the partial with y with respect to 1 minus x squared minus y squared. Of course, we know how to take those derivatives, and we find out that that's going to be negative 2x, and that's going to be negative 2y. All right, so now this is a vector function. Okay, they also call this a vector field. But that's a name for a different date. We'll study that more extensively some other time. Okay, so it should be noted that grad f, so that's often called grad f. That's how you would say that. Okay, grad f is very important in scientific computation. It's very important in scientific computation, particularly machine learning. Machine learning and what we call AI, artificial intelligence, all sorts of important applications are all related to Gradf. Gradf is a really important tool used in those things. So what does this give us? So let's ask a question. Why is Gradf useful? Okay, I said that it's useful in these sort of commercial applications involving artificial intelligence and machine learning. That's great, but let's maybe talk about something a little bit more specific. So recall directional derivatives. So directional derivatives, we would call it df of u, where u is some direction vector. It's a direction vector such that u is a unit vector. Okay, and we know that df of u can be written as the partial of f with respect to x times a plus the partial derivative of f with respect to y times b. Well, if we look at this, this looks like a dot product. So now we actually have a new way of writing this. This is actually grad f dotted with the vector u. Like that. So maybe we'll write it out fully. Okay, so this is a useful notation. All right. What else can we do with grad f? What can we do with the gradient vector? Turns out it does a lot of really great things. So I'm going to ask another question. And this question is, okay, so grad f is this fx, fy, that's the other way to write derivatives. Okay, and this sort of points in some direction at every point in xy space. Okay, in some direction. And in a direction, it's going to be in the xy plane. Okay, so one way to think about this is that, of course, we have our z vector, we have x and we have y. Let's say I pick a point, x comma y. And of course, we also have this surface, right? So this is the surface. This right here is the function z is equal to f of x comma y, right? So the question I have is, grad f can be thought of as a vector in the xy plane. What direction does it point? Surely it points in some direction in the xy plane. What direction does it point in? Well, it turns out there's a really cool answer to that. So grad f always points in the direction of steepest ascent on the surface of z equals f of x comma y. So if I take the point that I'm at, xy, and I look at its z value up there, right? And let's say that the surface is going on some angle upwards, and I say, well, it actually seems to be pointing, if I'm at this point right there, it's actually going to be pointing in that direction because that is the most uphill direction. Okay. The most uphill direction. The steepest uphill direction. Okay, that's cool. So that's a colloquial way of understanding it. The other way to understand it is if you're looking at a map, a contour map. So if you're looking at a map from above, so here's X and there's Y, and let's say, there's all sorts of maps. You've probably seen maps, if you've ever gone hiking and you bring a map of the trail that you're on. All right, so we'll say right there, that's maybe the summit. Of a mountain. So if that's the summit of the mountain, let's suppose that you're right here. Well, the direction that we'd be pointing would be right there. That would be the direction. That would be grad F right there. Likewise, if I'm there, I would be pointing up that way. If I were there, I'd be pointing up that way. All of those are grad F directions. Okay, for every point. So here, you're going to be pointing up that way. Okay, it doesn't mean you're going to be pointing directly at the summit, but rather, if you were hiking along some on some surface, some mountain say, if you looked at the local slope on the hillside that you're on, the gradient F would point in the most uphill direction. So it would be so you can think of this as basically the mountain climbers. It's the mountain climbers vector. Grad F. Okay. So that's one way to think about it. And this is actually why it's so useful in machine learning. In many cases, what the application is basically one is trying to optimize some settings in a computer function. And what you do, of course, is, so you're basically, the question is, what's the best X and Y point? Well, we may not know that point. In fact, our function can be very, very complicated. But the idea is that you start somewhere at X naught and Y naught, and then compute grad F at X naught, Y naught, and then you go in that direction. A little. And then do grad F. So you go in that direction a little to call it X1, Y1, and then do it again. And this way, you can think of it like this. Perhaps you start down here, and you take a step that way. And you go there, and you take another step. Each time you take a step forward, you just check the gradient vector and go in that direction until you get to the top of the mountain. So that's not a surefire way to get to optimize a function, but it certainly is a viable answer. It should help give you an answer using this method. So it turns out that machine learning uses that technique extensively, particularly in things called neural networks. Okay. All right, so one more question now. Okay. Why does Gradf point in the direction of steepest descent? All right, well, we can actually prove it. So Gradf is going to be equal to fx, fy. Okay? So we can always write this as follows. This is going to be equal to the magnitude vector, Gradf, times cosine of some special angle. I'll call it theta star. All right. So the idea here is we're at a specific point, call it x and y, and and our vector grad f is pointing in that direction, and we'll call that theta star. Now, let's examine all directional derivatives. So we're going to look at duf in this direction. We'll call it theta df. We'll call it d theta f in that direction. We'll look at all of them, and I want to know, is this specific one there better than all the others? So let's examine all directional derivatives. We'll call it d theta f. And of course we can put u, that's going to be equal to cosine theta sine theta. So what we want to know does theta star make u d, does that make the directional derivative, does that make it maximum? Okay. We want to know, of all the possible directions, is theta star the best one? Okay, so again, theta star is given. We know what it is. We can compute it. And now we're going to compare it with all other directions around it and see if it truly is the best. So this should be pretty straightforward. We know that d theta f is going to be equal to grad f dotted with the vector cosine theta sine theta. So that's going to be fx dotted with cosine theta plus fy sine theta. Okay, but we already have a definition for what the gradient vector is. We can write this as follows. That's going to be now grad f is going to be cosine theta star, comma, sine theta star, like that, dotted with cosine theta sine theta. We can write this as, well, so let's hold on to that in a second, but rather let's now take the derivative. We're going to take the derivative. We're going to optimize this as follows. So we take the derivative of fx times cosine theta plus fy sine theta. Okay, remember that fx and fy are not functions of theta. They're theta star, which is a fixed variable. So that's going to give us fx times negative sine theta plus fy times cosine theta. Okay. Well, there's our two things. And now, of course, we set to 0, and we try to find that critical point. And then we're going to find out we get fx times sine theta is equal to fy times cosine theta. We can change things around here even more and say that that's actually going to be sine theta over cosine theta is equal to fy over fx. And we know that that's going to be equal to cosine, that's going to be equal to sine theta star over cosine theta star. Okay, we can write that as tangent theta is equal to tangent theta star. Of course, we can now take the inverse tangent of both of those, and we find out that theta must equal theta star. Always. So that's a cool little proof that, yes, it should give you an extreme point. So this proves that theta star is an extremal point. It doesn't prove, though, that it's a maximum. It doesn't prove that it's a max or min, just that it's an extreme point. We'd have to go and then check the second derivative. We will not do that, but rather, okay, it's either the maximum or the min. Shall we do it? Let's see. We could do it, I suppose. Yeah, why don't we do it? Let's give it a go, I guess. So we can do that. That'll be now d theta squared is going to be of d theta f, and that's going to be, of course, fx times negative cosine theta minus fy times sine theta. But now we know that theta is equal to theta star, and that's going to be negative cosine squared theta star minus sine squared theta star, right? Okay. And so, of course, that is going to be equal to negative 1. So we know that this is concave down. This is the concave down second derivative, so we know that it's a maxima. So that does prove, in fact, that it is the maximum value and not the minimum. Okay, so that's a proof. Now, in the last little bit here, I want to just go over one example. So let's go back to our initial problem, our initial thing. I can actually plot this. It's a paraboloid. And it looks a little like this. It's kind of that gumdrop parabola shape. Goes down like that. So now we're going to look at, let's examine the point 1/2, 1/2. Okay, let's find out, let's find out what grad f of 1/2, 1/2 is. Okay, we can, and remember that's this point right here. We'll put it right there. That right there is 1/2, 1/2. And I want to figure out, if this is our surface, we expect it to be pointing in the most uphill direction. So it should be that it's pointing towards the origin. So let's see if we can find that out. Let's look at grad f. That's going to be equal to negative 2x, negative 2y. Cool. So now grad f at 1/2, 1/2 is going to be equal to negative 1 -1. Cool. All right, so my grad f vector truly is pointing inward from that point. So there's my grad f. It's pointed towards the uphill. So if I brought that point up, my grad f would be pointing that way towards the top of the mountain, if you will. So that just gives you another way to visualize how these functions, how this gradient vector works, and why it's so cool. So thank you very much.